But I will do a quick introduction.
I'd like to slide all together.
All right. Beautiful. All right. Welcome everybody to our special series, secret seminars, our mini course on Qbism. We're very happy to launch the series with Professor Rutger Schock from Royal Holloway, University of London, where he's a professor in the Department of Mathematics, I believe. But Rutger is a physicist and theoretical physicist working in a variety of areas of quantum information theory. And Rutger is a friend of the department. He was at one point a postdoc here many years ago, working in the area of quantum chaos and its relation to quantum information theory. Really incredible, beautiful work, and now one of the founding fathers of the school of Qbism. So we're happy to have you here. Let's welcome Rutger.
Well, thank you for having me here and giving me the opportunity to give this talk. Sorry that I didn't join the group meeting an hour ago. It was really a major faux pas.
No, and we didn't remind you that it's still happening 30 years later. But
this is the first of 3 lectures on Qbism. And I mean, part of the idea came from the fact that Qbism really started here. Well, not almost here. I mean,
You might have to click first with the mouse.
okay. Started there.
oh, yeah. That doesn't exist anymore.
Wow. Yeah, because when I came here a week ago, I was walking to that side and was sort of flabbergasted. So in 1993, exactly 30 years ago, Carl, Chris, myself, and Howard Barnum, we started to talk about probability and, well, how to interpret it in quantum mechanics. And so the thesis of this particular lecture is that the interpretation of probability matters. It actually matters deeply, both in quantum mechanics and in statistics. And this is really to counteract the common viewpoint that really how you interpret probability is sort of irrelevant for physics. So, very brief history. So in 2002, the first paper appeared on quantum Bayesianism by Carl, Chris, and myself. This was not yet Qbism. Then Qbism appeared in 2010 in this paper by Chris. In 2014, hit the world stage. David Mermin wrote a paper in Nature about Qbism. And so that's basically history. Now, I would like to tell you a little bit about being Qbism. The Wikipedia page about Qbism actually is wrongly titled quantum Bayesianism. So the B should not stand for Bayesian. And the reason is that Bayesian is a very broad term. According to the statistician I.J. Good, there are 45,536 variants of Bayesianism. And many of those are actually incompatible with Qbism. So it should not stand for Bayesianism. Qbism actually is rather close to the interpretation of probability due to Bruno di Finetti. So quantum Brunoism would actually be a better way. But the best possibility is quantum betabilitarianism. Because betabilitarianism is a term invented by Oliver Wendell Holmes, a former Supreme Court judge, and it captures the idea that the world is bettable. And that is, in some sense, the best two-word slogan to characterize Qbism. The world is bettable. But betabilitarianism is never going to catch on. So we have settled on E. So I would briefly present a few alternative interpretations of probability and basically tell you why they don't fly, very briefly. So it's tempting, especially for physicists, to regard probability or to define probability is limiting frequency. For instance, the probability of heads would be heads in a coin toss would be the limiting frequency of heads as the number of coin tosses goes to infinity. And that is sort of captured by the weak law of large numbers for fair coin. And here's a version of that. So for all delta greater than 0 and all epsilon greater than 0, there exists n, capital N, such that the probability that the relative frequency of heads departs from 1/2, that this probability is greater than delta is less than epsilon. So it becomes arbitrarily small as n becomes very large. So the observation there is that that is a circular definition because you actually invoke a probability here in this law. So that is not suitable to define probability. It's circular. Often people then appeal to the strong law of large numbers, which goes like this: the probability that the relative frequency of heads close to 1/2 is equal to 1 in an infinite sequence. But actually, you have to say circular probably because it's a probability here. And the idea that probability of 1 is something fundamentally different, and so you basically overcome this circularity in this is a fallacy. And I'm going to comment on that later, and Chris, I'm sure, is going to comment on the same thing. Yes, the subsequent talks. Here's an well, I mean, I'm going to do a little experiment here. So this is basically about another view of probability, namely this is that probability is something like propensity, something inherent to a situation or an object. According to Popper, I think that the propensity is going to Popper. So let me do an experiment. Let me toss a fair coin. It's very, very difficult to source this coin, actually. Nobody I asked had a coin. And so finally, I was lucky eventually. So here we go. I'm going to toss this coin. Heads.
Come on, Rosencrantz, is it head again? It's again?
Heads. Heads. So what's going on? I want to draw them. This is basically an experiment situation described by James in his great book on logical science. So the moral of this is there are people who actually can do what I just did. They can spin the coin in such a way that it appears to tumble and flip, but actually only sort of tumbles like that. So always shows the same side up, so they can actually make the coin appear heads every single time. I'm not claiming I can do that. But,
You just did.
especially the one where the idea is then that, I mean, the first observation is that probability of 1/2 is not a property of the coin because it depends on how I toss it. And if I toss it a particular way, it would be 1 if I'm very good. Right? So the probability is not a property of the coin. So what people can usually say is, well, you just step back and say, well, there's a property of the coin and the tossing mechanism. You have to just specify the way you toss the coin. Or precisely rule out the tricks like I just presented to you. But that's obviously not working because if you actually specify exactly how to toss the coin, well, then you will always get the same result. Because it's a mechanical system, and if you specify your initial condition precisely, you will always get the same result. And actually, there are coin tossing machines. I think it's who is it? Christian, you will know who has a machine like that.
Oh, Percy Diaconis
Percy Diaconis.
had one machined by the machine shop in his apartment.
Yeah.
And it always tosses it exactly the same way, even though it's flipping through the air.
Yeah. Okay. So it's not a property of coin tossing mechanism either. And so what James' conclusion was, and which is the correct conclusion, is that any probability assignment in these situations always starts from a prior probability. So you can, of course, specify the distribution of initial velocities and distribution of initial positions of the coin, and then you will get a probability distribution for heads and tails, but it depends on the prior distribution. Now, James he influenced, I think, us all very much even early on. But he is a proponent of something called objective Bayesianism. So he has spent a lot of time working on ways to actually specify the correct prior. Most famously in his principle of maximum entropy. And so I would like to just say something about why objective Bayesianism in the end is not coherent, or is not going to be the answer. So the idea in objective Bayesianism usually is you start from some symmetry principle, then you derive an objective prior. And James' Max-End principle seems to be of a different kind, but actually, if you look at it, always starts from a symmetry assumption about your initial measure structure. So you cannot just start the James from scratch. You have to start from an initial invariant measure of some kind. So you start from the symmetry principle, and then again you discover a hidden circularity, because symmetry principles used to derive objective priors have the following form. They say the probability for outcomes, say 1 to n, is invariant under permutations. Hence, probability of 1 is the probability of 2, etc., all the way through. And you see the circularity. Basically, you postulate that your probability is invariant under the symmetry transformation. So you already make a statement of probability to start from, and so you can actually derive from that. So it's again a circular thing. And so what I would say, or we would say, is that the invariance of probability assignments under a symmetry transformation is always agent's judgment. So that's not something you can derive. It's a judgment. It's an assumption. So then we come to the well, one thing I want to say briefly here is that all these considerations apply to classical world, classical mechanics, classical probability, and so you might think, and people have thought that very strongly even, that quantum mechanics is different. So even all this is true, and in quantum mechanics you cannot actually make sense of frequentism or of objective priors. Quantum mechanics is different, and this was something we definitely thought about, toyed with, and it was very difficult to get away from that idea. In the end, it turns out that quantum mechanics gives you even stronger reasons to reject all these objectivist ways of living probability.
I'm struggling with this a little bit, just because I like to think that uniform priors is total ignorance, and I can at least know that I am ignorant. Is that still circular?
Yes, because for the same reason, ignorance is just a word for saying my probability is invariant under the symmetry transformation. So I'd say yes.
Okay.
It's just a different way of, it's a way of hiding
the
circularity, just like symmetry principle itself hides it. So that's what was one of the big realizations on the way towards Qbism, is that quantum mechanics gives you even stronger reasons for the subjective view, which I'm now going to, or personalist view of probability, which I'm now going to briefly describe. So that goes back to the 1920s, Definetti and Ramsey, and then the 1950s when Savage actually turned it into a fully fledged probability decision theory, which then became very popular in economics. Here it is. So according to it, all probabilities, including those equal to 0 and 1, are valuations an agent ascribes to his or her degrees of belief in possible outcomes. Very mouthful. So the valuations have to do with money, if you like. And it's always an agent's ascription. An agent assigns probability. And it's about degrees of belief. That's the various ideas here. Now, the rules of probability theory are grounded in decision theory. How should I act? They have a normative character, but not describe situations. They're normative. How should I act? The word should relates to normativity. And they can be derived from a very simple normative requirement, no sure loss. This no sure loss principle is called Dutch book coherence. So, how do we define probabilities in this context? I mean, Savage has quite a elaborate way of embedding it into a full decision theory, but you can have a very simple version of that. And then it becomes just the price of a lottery ticket. So here it is, my probability of an event E is equal to P. If I regard P dollars, between $0 and $1, as the fair price of a lottery ticket that pays $1 E or tax. That would be this definition of it. So how does this get off the ground? Well, here's an example for a Dutch book argument, which is adapted from Wikipedia. So this is a horse race with 3 horses. There's no other horses in the game. And the odds offered, even odds on horse 1, 1 to 2 on horse 2, 1 to 3 on horse 3. Okay, and I am a very sophisticated gambler, and I have a compound bet. So I say, well, look, I mean, I bet $100 on the first horse, 80 on the second, and 60 on the third. And so I thought about this. Okay, good. And so I'm basically paying for, I'm betting a total of my stakes of $260. Well, let's analyze the situation. There are 3 possibilities. Horse 1, horse 2, either horse 1 wins, horse 2 wins, horse 3 wins. And so if horse 1 wins, well, it's even odds. So the payout is $240 for horse 1 and nothing for the 2 others. So a net loss of $20. Horse 2 wins, well, I bet $80. 1 to 2 were the odds. So the payout is $240. Again, I have a net loss of $20. And you won't be surprised to see that in the third case, I also have a net loss of $20. That's worrying, isn't it? That's a sure loss. There's something wrong with all this. You could say it's about because, I mean, maybe I thought I was too clever and this compound bet is just a bad idea. But the problem actually lies somewhere else. It lies in the odds. First remark. So this is remarkable because you see, a physicist is usually thinks about probabilities always in the long run. So why is roulette a bad idea of playing roulette? Not because you might not win big in one spin of the wheel, but because in the long run you're likely to lose. This is a single shot. A single bet, you will lose $20. Okay, so what's the problem? Well, just look at the implied probabilities. I'm just rewriting the odds as probabilities. 1/2, 1/3, and 1/4. Well, they add up to more than 1. Okay. So these are probabilities where do not, or where the probability of the whole thing, horse 1 or 2 or 3, being mutually exclusive events is 1, and these 2 probabilities don't add up to 1. So they violate the laws of probability. Okay. And now that is a sure loss, and we're saying that this book, these odds offered, they're called a Dutch book. So Dutch book is a set of odds offered that lead to situations, well, you could say, where there exists a compound bet that leads to a sure loss.
Was this come up by the English or something? Or do you know where the term comes from?
That's a good question.
But I don't think the Dutch.
What makes it Dutch?
Yeah.
So they raise or lower the price.
Well, I mean, maybe
No.
Dutch are particularly risk averse. I once talked to Dutch people about it, and they thought this was a reasonable assumption, but no, I don't know the origin.
I've heard that it had to do with like if we're bidding on something, you can keep going higher and higher and higher until sold, right? That's the one you hear about. Dutch book I've heard is the other way. They started a high one and then there's a reversal of it or something like this, and that then you're guaranteed at least your price. I say $1 billion for this, peanut or something like this.
Maybe a Dutch person would only bet if they win in every single which would be the case.
So the Dutch auction is supposed to be better for the seller because you get your high,
It could be a slur by the English. Because, they're pretty close to each other.
Yeah.
There's bound to be friction.
So is this telling us that this bettor isn't using conditional probabilities correctly, and is that the lesson, or is there a more fundamental thing here?
Not conditional, just probabilities. It doesn't. Okay. Basically, he writes some probabilities. He uses for his betting, for his decision making, he uses probabilities that violate the laws of probability. That's it. Because these probabilities here, they guide your decision making.
Yeah, well, it's clearly he's not supposed to add these probabilities. It doesn't obey the law of total probability. But if he added them using conditional probability theory, it's either 1 or 2 or 3 win. You can't have a situation where all 3 of them win. And so knowing that, could he have chosen his betting strategy better? Or
there are bets that don't lead. For instance, if you just bet only on house 1, there's no sure loss. You might win, right? So it depends. So the statement is there exists, if you violate the laws of probabilities in your betting odds, then there exists a compound bet that leads to sure loss. And that, if you want to use them as a basis for your decision making, is clearly bad, right? Because you do not want to have to think about other things. You say these are my probabilities, and they are my guide to my decision making. That's my rational principle. So therefore, this is a bad thing if it exists. And so here's the definition. The agent's betting odds are called Dutch book coherent if they rule out the possibility of a Dutch book. And such betting odds exist. And this theorem, an agent's betting odds are Dutch book coherent if and only if they conform to the standard probability. It's actually a very easy theorem. And so therefore we cannot this Dutch book derivation now results in a theory with a normative character. Actually, the only axiom is you should not assign probabilities that lead to a sure loss, can lead to a sure loss. And from that, you can actually derive the probability rules. So, and these probabilities also have a normative character. You there?
I think I was describing Dutch auction and English auction, not necessarily Dutch book. I don't know. I don't know about gambling.
This is much simpler.
So if the probabilities don't add up to 1 and is less than 1, is there always going to exist a way to have a sure win?
Yeah, and that as well. You just turn the other way. So basically, you swap seller and buyer. So
Okay.
then
Okay.
they can have the same thing.
That's also sure loss or sure win. Or
Yeah, no, sure. It's always about
A
the
sure loss
possibility of
for
sure
one
loss.
means a sure win for the other.
So you can come up with a compound bet with a series of transactions, and they can involve selling and buying, selling or buying and buying. And so if you just stop
I
selling
see.
and buying, you get
Okay.
So who
I
made
just-
up this, do you know who made up this argument?
this was the Dutch book argument.
Because that might lead to who actually named it.
Dipinetti and Ramsey both.
Okay.
Independently.
Yeah.
And historically, nobody knows, as far as I've been able to search out, why it's called Dutch book.
So I'm just putting these rules down here. First, to emphasize that there is no Dutch book argument for infinite for constant additivity. So we just have only finite probabilities here. But I believe that's fine because you just use infinite sequences as a convenience. So in Qbism, the modus is finite. That's the finite numbers of outcomes. And the third one is this Bayes rule thing here. So in standard probability theory, this is usually used as a definition of P of P given A. And here's a theorem, because P of P given A is defined independently. And here is the definition. So P of B given $8. So again, between 0 and $1, right? It's my fair price for a lottery ticket that pays $1 if both A and B are true, both A and B occur, and refunds the ticket if not A occurs. So basically, if not A occurs, well, this probability is not going to tell you anything, right? So you just get the ticket first time. If A occurs, sense probability of B. So that's the sound. So it's a definition of conditional probability, which and then you can actually derive Bayes' rule from a Dutch book argument showing that it is violated. You can always make a Dutch book.
The second one is an or, right?
So yeah, in both sense. So yes, absolutely. I was so happy that I found the symbol, latex symbol, everywhere. Yeah, otherwise called V.
Yeah, it's weird.
Okay, so here's a remark about frequencies in nuclear trials, because obviously in physics, in lots of other situations, I mean, you often use probabilities when there are repeated trials and when you have frequencies. So what can I say about that? Now, basically,
Can I ask a question?
Yes, of course.
Does the normalizational properties for your exclusive and exhaustive events follow?
yes, I think so.
Could you repeat the question?
The reason, if I heard it correctly, is that the normalization of exhaustive and mutually exclusive events, does it follow from this? And yes, it does. I mean, basically, this example here was just one where that was violated. Because these three horses are supposed to be exhaustive and mutually exclusive. So therefore, this should sum to one, but they don't. It's really much.
Well, that's the statement that they should be normalized. I'm asking, do they follow from 1, 2, 3?
Yes. Yes. Definitely. Yes, because so you're saying that. So you think I should I possibly add one that P of the whole event is equal to 1. Maybe you have to do that. Yeah. Okay. I think you're right about that. So there's one axiom missing.
Maybe. John says no.
Oh no, I don't know that. Okay. It's not important for what I'm saying. So I'll carry on. Frequencies, identifying frequencies with probability is just a category mistake. No, actually, no pure mathematician would make that mistake because probabilities are measured and frequencies are data. It's just different. They're just different things. Frequencies are events and probabilities are measures. So, the Bayesian approach just makes this clear, just keeps a distinction. So, and of course, frequencies are very useful for updating probabilities. So you can assign probabilities to frequencies as is done in the law of large numbers. And you can refine your probabilities based on frequency data, and this is often done, but they're just different things. And something that Chris is going to talk about, the Finetti theorems give you a beautiful connection between this viewpoint and frequencies. So there is a exchangeability, the idea that measurement outcomes don't depend on the order in which you look at the system, and this applies to infinitely many trials. It's called exchangeability that characterizes repeated trials in this formulation. And in a usual physics approach, you have a primitive concept of a repeated trial, of an experiment that is repeated under the same conditions. Because any experimenter will tell you that's actually very hard to achieve. It's also hard to define because such a definition has to be circular. So you make it a primitive, which is actually quite vague. And whereas here we can actually say very clearly what we mean by exchangeability. this symmetry, and probabilities being invariant under certain symmetry. And this leads to a classical definitive theorem and also to a quantum definitive theorem, which proved what Qbism and I probably about 20 years ago. I'm just going to say more about this, but this is a way of actually characterizing repeated trials in a way totally within quantum mechanics, totally within formalism.
Can you see a little bit what you mean by the D row there? I'm just a little confused how to read this guy. So you can exchange measurement outcomes of some density matrix rho.
Well, you have many systems.
Many systems.
And so the idea is that your density operator is invariant under sorts of systems. And then you actually get this representation, this representation here. Then if this exchangeability condition, which I haven't spelled out formally yet, holds, then you can write this density operator in this form, where that invariance is manifest, of course, right? Because that was, and the rho is just some measure over the scale of which.
Okay. I'm just weird that there's not like some probability in front of it. So, okay. Yeah.
I mean, that's okay. I mean, this was hidden here.
That's hidden in there. Okay. Yeah, okay.
So is exchangeability an example of one of these symmetries that only has an epistemic meaning to agents that you were talking about before?
Well, I would certainly say that. I mean, an objective basis with differentiators, but yes, it is always the judgment of an agent. Okay, here's a variable probability 1. Even probability 1 judgments are judgments. It's important to point out because often people think probability 1 is sort of a connection to logic. Probability 1 is defined exactly the same way as any other probability, namely by a price I'm willing to pay for tickets. So if I'm certain that a horse named Albatross will win, writing down P of A wins is 1, this means that I'm willing to pay any price less than $100 for a ticket that pays $100. So,
Maybe even 100.
yeah, well, pointless. So, yes, you could say this, but I actually prefer this option. David Merman is adamant that this is the correct option because there's no, I mean, there's no reason for you to buy a ticket. So the formalism doesn't tell you that you should buy the ticket if it's the same. So it's a fine.
Like, doesn't this kind of way of trying to define probability face the problem with the St. Petersburg paradox? Because, like, I assume you know the paradox where the expectation value of the win is actually infinity. So, like, any finite price for the ticket would actually be reasonable, but like it actually never happens. So, like, what's the like?
Does that fall on the prior? If you
So the bet is just that, like, you're supposed to flip a coin like as many times as long as you're getting heads, and if you win, like if you have k consecutive heads and tails at the next one, then you're going to win 2 to the k dollars, and like the expectation value is, that happens with exponentially small probability, but the price you get is also exponentially higher.
Yeah.
So
that's usually dealt with in a fuller decision theory where money has no linear utility. So with this assumes that it's the first million is, or the second million is just as valuable to you as the first million is. But of course it isn't. In the practical economic decision problems.
sure, like I guess those would be
utilities
like the practical resolution for
and
like
that
an
would-
economics point of view.
Exactly.
But like,
Well,
like,
this is why I mean, my biology is saying this is basically built up by Mickey Mouse version of the
actual Qbism or
not Qbism, the actual derivation of the probability calculus from decision theories. Because this assumes linear utility, which is clearly not realistic.
So you're saying that like in this framework of defining probability, you actually have to like go through full decision theory in order to define probability.
Yes, sure, yeah.
Okay. That sounds like a big machinery for defining probability from a frequentist point of view, where like that, all you're saying is like, as long as the probability is like close enough to 1, you're like pretty sure that's gonna happen. And like if it's small enough, then you're pretty sure it's not gonna happen. And that,
founded on something circular.
no, but like in that case, like you can actually avoid the circularity if you just say like it's gonna happen.
It's
And
called,
one's like
whose principle was this? There was a principle of moral certainty, right? If the probability is close enough to 1, something's morally certain to happen.
I would say like
pee in the bowels of Christ. I'd be whoever said that, that's his principle.
Rudiger, I think you might have said something about this. I didn't hear. Why isn't that less than or equal?
he said.
He did, because there's no
He's
should
got a
with
minute.
it.
Sorry, it's not important, and I'm going to move on. So basically, the point is that here for ontology of things, this does not mean probability A wins because I have these betting odds. It does not mean there's an objective feature of the guarantees of the possibility.
But what if you're betting on some horse wins? One of the horses in the race wins. That does appear to be an objective feature of the world.
Well, no, it might not. I mean,
They might all break their
they might all
legs
break their
before they get
legs.
to the finish line.
This actually has an important consequence of quantum mechanics. I mean, all the EPR criterion of reality. It reads like this from the EPR paper. If without in any way describing a system, we can predict with certainty that is with probability equal to unity, value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now, this is crucial in lots of papers and derivations having to do with dynamic quantities. And you can see immediately that if you deny that probability 1 implies an objective feature of the world guaranteeing the outcome response. So Qbism rejects the criterion of reality. I'm not sure Chris will say more. Okay, now let's come to something much more mundane. This actually harks back to a few lectures I gave 29 years ago in 2014. I just sort of.
I always say start with 19, never start with 20. That's just all that.
Yeah, it's disturbing. Yes. So this was about classical statistics. So hypothesis testing. Now here we go. The sensible Bayesian way of doing hypothesis testing, and if you think this is a little opinionated, what it is, but I actually stand to these opinions. I think there are very good reasons for that. So the setup is you have a null hypothesis, you have an alternative hypothesis, which is what you're actually interested in. You want to find reasons for believing in it. You have data. The Bayesian has a prior probabilities for the alternative and the null, and then one to 1. You have so-called likelihoods, which are the probabilities, and the model, the statistical model. You have probabilities for the data given the alternative hypothesis, probabilities that they given the null hypothesis. And then the Bayesian simply applies the Bayesian rule and comes up with given the data. If you do the experiment, you collect data, and then you condition your probability on the data, use Bayesian rule, and that gives you your posterior. And that's it. So you now have a probability. What's the probability for A being true given these data? Good. Okay. Simple, very straightforward.
No, I'm just thinking.
Good. So here's the frequentist. Mainstream hypothesis. This is mainstream because generations of people, non-mathematicians, medical students, sociologists, but it's actually not a joke. I mean, I've learned it, and so this thing is incredibly emerged, right? because this, I mean, people have learned this, and then when they go through a career as professors of medicine, and shit, this is what they know. So this is a major problem. I'm going to show you this. So according to frequentism, these probabilities, a given data and any given data are meaningless for frequency interpretation. Because the A is either true or false, it's a single shot thing, there's no frequency here. So you have to actually work with the likelihoods. You're giving it the frequency. Fine, there's no problem with that. So here it is, so then you do something which is, you identify tail areas of your likelihood function, and you regard them as extreme outcomes. So there are outcomes to extreme as you think they're unlikely, given that the nervous system is true. So you identify these, and typically you have one-tailed or two-tailed things. Okay, and now you choose a significant number, alpha. Typically that is a 1% or 5%. Then you run the experiment, collect data, called D0. Then you compute something called the p-value, and the software does it for you, which is, this is also defined, p0, the probability that if you run the experiment again, the data would be more extreme than the data we actually observed. So this is the probability that in a new run of the experiment, data will be more extreme than D0, the observed D0. But all this given the null hypothesis, because this is the likely function. This is all standard statistics. And then you reject the null hypothesis if P0, this p-value, is less than or equal to your significance level. And the argument is, well, that just means that these data are actually pretty unlikely given the null hypothesis. So I think the null hypothesis is wrong, and I have some evidence for my choice. And the justification is the probability of rejecting a true n, a true null, is alpha. This is all perfectly sound. It's true. The probability of rejecting a true n is alpha. So if you follow these prescriptions, and let's say you choose your alpha equal to 1, you will make a wrong decision only in 1% of the cases. That's a sound approach. Yeah. Okay, let's look at XKCD. P-value hacking. Jelly beans cause acne. Scientists investigate. Okay. And then they do, and they found no link. The P is greater than 5%. Okay, and then the girl says, well, it's only a certain color that causes it. Okay, they go and investigate. And they investigate colors. It's hard to read. It starts with purple, brown, pink, etc. They have P within 5%. I mean, it's a total of 20 times, which is not a coincidence. And once we found a link between green jelly beans, P less than 5%. Okay, that's called p-value. Use green jelly beans linked to acne. 95% confidence. Only 5% chance of coincidence. Then, so we did the clean study again and got no link. It was probably, and then media shouted again, research conflicted on green jelly bean acne link, more study recommended. It's all total problems. Okay, so what's the problem? Okay, I mean,
I do recommend you stick with jelly beans and never do that for M&Ms.
So here, one of the most cited papers in 2014 was this one here. It's hard to read, unfortunately. P-values, the gold standard of statistical validity, are not as reliable as many scientists assume. It's the title of the paper. I mean, it is pretty restrained, but it makes very, very hard-hitting points against statistical practice. It's not against what I just presented in my slide. That was all totally sound. Right? If you do it like this, just as a decision procedure, it's fine. Okay. Here's 2016. I mean, look, this is all 25 years after I gave my talks. Even then, this was utterly clear, all of this, right? But it took them this long, longer, because these things were known even 20, 30 years before that. So they came up with this statement. P-values can indicate how incompatible the data are with a specified statistical model. Now that's the I put it in red because it actually, I mean, apparently this was a very tough discussion. There are Bayesians in there and frequentists. And so the Bayesians would never have agreed with that, right? Because this is not how you use p-value in the theory I showed you. The other one, so p-values do not measure the probability that the study hypothesis is true, or the probability that the data were produced by random chance alone. I mean, any probability, of course not. Look at it, the likelihood of some, there's some sort of completely different thing. But people assume that. People think that's what it means somehow. Conclusions should not be based only on whether p-value passes the threshold, and proper inference requires full reporting of transparency, which of course would have dealt with that p-value. I mean, that's very sound. So what's the problem? Why is that even a problem? Well, there's nothing wrong with decision space of p-values, as I showed. But users of statistics want more than just concluding the null hypothesis was rejected 51%. They want to know how strongly do the data actually confirm the alternative. So they want the probability that the hypothesis is true, which is only the Bayesian can give. They have the p-values, so there's someone thinking, well, that's just the same thing, which it isn't. That's the problem. And so here is 2020 paper, Bayes formula, powerful but counterintuitive tool for making decision making. I mean, counterintuitive. Look at this. Compute the p-value. P probability of D is more extreme than D naught given N. And here is Richard Jeffries on this. What the use of p-values implies, therefore, is that a hypothesis that may be true may be rejected because it has not predicted observable results and has not occurred. This is basically in words what we're doing up here. We are looking at the probability that second velocity experiment will give us data more extreme than what we actually observed. So, I mean, that's counterintuitive. Anyway, it's a good decision procedure, but P is not a measure for how good, how strongly the data. Now, I'm giving you, let me see. Yeah, I can do that. I'm giving you two some notes from 29 years ago. So I just.
Oh my God. That's awesome.
So my data are NK, so it's N trials and K successes, right? This is what that would be. And so you have likelihood functions on the left given the alternative, on the right given the null hypothesis. Okay. Then data in this case, because if you assume the number of trials given, and data is just K, this is along the x-axis. So I have various possibilities. And so K1 and K2 are just example outcomes I get, and it's KC, critical number, and alpha 5% is the area to the left of this. This is my tail area. And so the decision procedure is simply I accept the null hypothesis if my observed K is greater than KC, so if it's actually outside the tail area, and then reject my null hypothesis if it's inside the tail area. Now, so that's what it says. Beta, I'm not going to. Beta is the power of the test, which is 1 minus probability of making the other kind of error. It's fine, but so the point. So this is the decision procedure, and you can immediately see that the p-value does not really tell you anything about how strongly particular data, particular example, reject or support the hypothesis. For instance, if you are just in the middle, so if K is equal to KC and you reject the null hypothesis, you see the likelihoods for alternative and null are the same. Right? So Bayesian would say, well, the data are actually totally ambiguous, but this is rejected. There's no contradiction here, no problem, because it only happens 5% of the time. So, and even Bayesian might be wrong about the conclusion, but still. So that's what happens here. Now, you can actually put this to an extreme. If you have very large sample size, these two distributions would actually sort of move apart, right? They have less and less overlap. So my tail area, 5% tail area, now you see is here. And now, if I actually if I get this result here, I will stay rejected at 5% level. But if you see the probability, the likelihood for given the null, it's much bigger than the actual given the alternative. So the Bayesian would say these data very strongly support the null, whereas the orthodox rejects it at 5% level. Which again, it's not a contradiction. Right? It's a coherent paradigm. But what this highlights is that P cannot be used as any measure of how well the data support or reject the hypothesis. Because here the data says something completely different. So that's what the problem is the misuse of P value. And I mean, I would think that probably 80% of all studies that are published, medical, secondary, etc., have problems in this way. Because it's just a very, very long okay.
But my favorite in very recent history is that the Department of Energy has recently reported with low confidence that COVID most likely came from a lab in China. What does that mean?
There's lots more things to say. Significance, high significance, and it's a bad word because the effect might be tiny, but it might be with very large significance, but it doesn't mean significant effects. The language gets in the way.
Yeah.
The other thing is if you have, let's say, if you have one outcome which is significant, one is insignificant, right? So you have one supports, one doesn't support. What do you do? How do you actually combine these things? So basically, this is very easily. Here it's very hard to do this. There's a whole big theory about how to possibly do that. Because the idea is that you actually design the experiment beforehand and then you run it. You can't change it. Optional stopping is another one. You run the experiment, it's only mathematically sound if you choose the sample set at the beginning. But then after half the sample size is gone, you see that all patients for one procedure die and all the others survive. So it's clearly not ethical to continue. But the theory doesn't tell you how to actually report the results. So I should say this is Lindley's paradox. So this example is issued to Lindley. It's not really a paradox, as I said, because it only highlights that the p-value cannot be used as a measure for how well the data support results. Here is my this is a plug for this talk. So Conaghan provides even more compelling reasons for talking person-based approach, and this is Chris's lectures on the right.
Further questions?
Yeah, I got a quick question. So when you were talking about the decision theoretic way to define probability, are you and you said something about the utility function rolls over. So are you assuming sort of the well-ordered axiom on the set of all possible like choices that you can make? Okay.
Unfortunately, yes, that is a very strong answer.
Yeah, it is. That's why I was like, when I was going through my food.
I just need to have these 3 coins to press. Because you might need them.
Oh, thank you. You guys, I give them back to.
I have 2 bonus slides, which I don't have time.
These aren't your coins.
No,
They're mine, but you can have them.
I can have them.
Yeah, fine.
I just started setting cards in spike over here.
Yeah. Don't spend it all in one place.
So
Kind of hard not to.
this is going to show you, I believe I'm just saying, it's a rotation experiment with coins. Just be very, very nice. And put a like nice bonus.
So I hear the echoes of my philosophy professor from college combating utilitarianism with like, my tooth hurts. Maybe I want my tooth to hurt. So, Bayesianism says, okay, if I want to be right, this is how I should assign probabilities. What if I don't care if I'm right or not? What if I want to be wrong? I guess that's what I'm struggling with as putting in the normative, the offness.
Well, I can say it gets worse. It gets worse in Chris's talk, because then we have a normative principle, which is, which is a law of nature. So I mean, this normative principle here, I mean, you're the first one who actually, I've never heard to challenge it. I mean, if you want to do economics, or I mean, this principle that you should try to avoid a sure loss seems as uncontroversial as it gets as an object principle. But yes, I mean, you can certainly challenge it.
You're a philanthropist. You're trying to get rid of your money as fast as possible because it's the root of all sin. You know.
But that's a different thing from assigning, all the Dutch book argument says is if you want to avoid a sure loss, you must obey the
Yeah,
rules
if you
of
want.
probability theory. It doesn't say you can't use stupid probabilities. You bet on a horse that's already broken its leg before it even leaves the gate. You know, that's fine, you can do that.
One more? Go for it.
So you said that at the beginning that B maybe should stand for
Benevolent.
benevolentarianism or something like this, right? Yes. And so I've heard this story many times from the Bayesian perspective that, you know, one of the great merits is that you can relate it to sort of with money. You know, you put the dollar signs, there's some sort of betting and utility and all of this. But then at one point you raised an counter argument to somebody saying, well, this really depends on your theory of economics, you know, and so you feel like you made some progress by offloading the difficult problems to economic theory, but then when challenged, you say, well, but then really, do we really believe the second million, million has the same value utility as the first million?
It's not straightforward, but I mean, the remark about it depending on the axiom that you can achieve all actions can be ordered. That's the answer, because that's actually pre-economical. So if you start with the axioms and then some other assumptions, for instance, no sure loss, you can derive that this ordering of actions is equivalent to maximizing respective utility. So you derive the utility function and probability function at the same time this way. And then you can, utility functions, of course, just a function of numbers, and you can call this dollars for that. It's not necessary. Yes?
Is there a way to do it with maybe some sort of like local or not using a total ordering on the setup? Just because like it's kind of a strong assumption to assume that you can look into the future and see all possible choices you can make, and you can order those decisions by what's like.
There is work on that in economics, but I'm not very familiar.
I think we'll leave it there and thank Guido for a great introduction.